So we'll start off with 1 at the top, and I'm going to record the probabilities here. So I have 5 vertices left. Say we put the vertices 2, 3, and 5 on this side, and we're going to put the vertices 4 and 6 on this side. What's the probability of that step? Well, I'm essentially picking out a subset of the numbers 2 through 6, of those 5 numbers. How many subsets of 2 through 6 are there? 2 to the 5th. So the probability of picking out that particular subset is 1 over 2 to the 5th, right? 1 over the total number of subsets of a 5-element set that I could have picked to go on the left. Of course, we don't need to worry about this, because once we pick this guy is automatic. It's just the rest. So now we do it again. So we've got to have 2 here, we've got to have 4 there, and now we've got to partition 3 and 5, so we might put 5 here and 3 here, say. And then we've got to put 6 and its complement, the empty set somewhere, say put the empty set here and 6 there. So what's the probability of doing that? Well, now that 2 was fixed once we had this partition, and then we had 2 things left over. So the probability of splitting them that way is 1 over 2 squared. And after we put the 4 here, we only had 1 thing left over, so the probability of putting it on the right rather than on the left is 1 over 2 to the first. And now we're done, right? Because everything else, we're just going to have partitions into empty sets. Don't really do much. So all those partitions are 1 over 2 to the 0. We don't have any choice because we're partitioning down. But now again, think what the hook lengths were for this tree. Right? Top vertex has hook length 6. This has hook length 3. This has hook length 2. These guys all have hook length 1. And you'll see that this is clearly the product over all these vertices of 1 over 2 to the h of v minus 1, right? 6 minus 1 gives you the 5. 3 minus 1 gives you the 2. 2 minus 1 gives you the 1, et cetera, et cetera, et cetera. And it has to be, because think about it. What is this 6 telling you? It's telling you that that vertex has 6 descendants, including itself. So if we're partitioning the set of all descendants not including itself, we're partitioning one less, a set of size 1 less, and that's why you got the 2 to the 5th, 1 less than the circle. And similar for the rest of these. So I hope it's clear now that 1 there is trivial. I mean, it's directly from the definition of the algorithm. There's nothing more to do. We've built it into the algorithm. We've hardwired it. There's nothing more to do. So 1 is clear. And 2 is easy. So 1 is trivial and 2 is easy, which is the way I like my proofs to be. So why is true easy? Well, let's take a look at this.
Why is it not clear? Is that probability?
I'm sorry, what?
The probability distribution, so it has to add up to 1.
Well, we don't know that. We haven't proved that that's
Oh,
the case, right? That has to be proved. We just say, put things down with this probability. Well, it's possible we got something which wasn't a probability distribution this way.
Yeah, not clear.
There is something. Just because we define something, it doesn't mean it's correctly defined. We chose to look at it that way.
But the probabilistic process is clear a priori that has to add up to 1?
In my mind, I mean, we could have defined all of these probabilities to be 1/3, and then of course it wouldn't, they wouldn't sum up to 1. But we define these probabilities any way we like.
But you decide, you like flip a coin, decide on the left side, and then.
I mean, yeah, I think what you're essentially thinking would go through.
Or you could have phrased it differently.
Yes.
And then it would be built in.
And then it would be, yeah, because of the way I phrased it, we do a little bit more work. But yeah, if you think of it as just for each one thinking, do I put it on the left or I think I put it on the right, and you've got a half for each one. In fact, if people are willing to accept that as equivalent, we can go on. Does everybody see what Donald is saying? That essentially, to get this 2 to the 5th, you can think of it as saying that for each element, now think of this element-wise, rather than just thinking of the whole set together. For each element, I'm picking for it to go on the left and the right. So the 2 goes on the left or the right with probability a half. 3 goes on the left to the right with probability a half. 5, right? And since each of these have individual probability a half, the total has a probability of 1 to the 5th. And then it becomes clear that what you're going to get has got to be, right? Because half is equidistributed on both sides, and therefore things have got to work out. So I was going to give a formal proof of that, but this is perhaps even a nicer way to think about it.
So if you do a loaded coin, can you get something more general?
Yes, you can. If you do loaded coins. So there are these Q-hook length formulas of urine and wax. Essentially, you get them by taking a loaded coin. Okay, good. So 2 is now also good. Thanks to Joel. That's how you say thanks. Okay, so now I can talk to you about the question, why is this, do I like this algorithm better than the algorithm that I originally showed you? It's because of the following. So here's some notes. Postscripts. First of all, this formula wasn't the only formula that Han had in his paper. He had a second formula. I would like to introduce this to you now. And you just need one small bit of notation, definition. So the completion, I'll call it T hat of a tree T, is gotten, so if T is, say, has n vertices, is got, and if T has n vertices, this is going to have 2n plus 1 vertices. Okay. Is gotten by adding all possible leaves. So for example, suppose I start with this tree. What is its completion would look like? Okay. Well, this vertex already has both of its children, so I can't add any leaves here. Here, however, I don't have any children, so I can add both possible leaves. Here, I have one child but not the other, so I can